So the third method of non-destructive testing that we're going to look at is liquid penetrant inspection. You'll also hear it referred to as dye penetrant inspection. So we're going to be using a dye or a liquid to find cracks. And the picture shown here, there is an example of what a indication of a real indication looks like, a crack indication on a part. So starting off, looking at why we use it. So LPI has some very strong advantages. It's probably one of the most common, besides a visual inspection, it's probably one of the most common field or in-service inspections that's performed in aviation. The first part of it is it's extremely reliable. It gives good indications. It's fairly easy to repeat tests to get the same indication, or to get the same indications, or to monitor a part or a component over time. So like I said, again, it can be fairly easy to perform. There's a few different methods and versions of it, and so some of them are harder than others, but the ones used most commonly in the field are fairly easy to perform. It can be fairly inexpensive. The portable visible dye inspection uses basically three aerosol cans that are anywhere from $10 to $20 a piece. So you're talking, to get started, you're talking $20 to $30 total. If you're doing, it's a little bit more expensive to do fluorescent inspection. We'll look at that, which is what aerospace requires, but still the materials aren't that much more. Again, $10 to $20 per can, three aerosol cans. But you do need a black light in that case to be able to do the inspection. So a portable black light flashlight, you can get those fairly inexpensively nowadays too. There are more sensitive versions that are much more, more expensive, or more expensive to set up, but cheaper to do if you're doing a production run where you have like a test bench and all that kind of thing. But they're it can be very sensitive. We'll talk about different levels of sensitivity. And it can be done fairly quickly. So it's not quite as quick as a detailed inspection. It's not quite as quick as mag particle because there's some wait times involved in the process. But someone that's experienced at it and has a process that can be done fairly quick can get it done in about 20 to 25 minutes, including the 20 to 25 minutes, probably about 30 minutes when you include setup and time to look at the results and then do cleanup and all that stuff. Disadvantages with liquid penetrant inspection, it is only going to find surface flaws. You have to, when a liquid sprayed on the surface isn't going to be able to work its way down into subsurface flaws. It does not work very well on painted surfaces. They can cause issues with it, especially cracks or crevices in the paint can give indications of flaws, or paint that's covering a flaw can hide something that should give an indication. You have to make sure things are clean. You don't want any chemicals or residue on the part. One, because it can obscure indications, but also because they can react with the chemicals you're using and possibly cause them to break down or not work correctly. When we're cleaning, we can't use mechanical cleaning methods. Mechanical cleaning methods are things like shot blasting, bead blasting, or walnut shell blasting, that kind of thing, because those actually have the potential to peen close the very small cracks that we're doing. So if you use metal media for cleaning, you can actually kind of mush the surface, mush any tiny cracks closed, and then the dye doesn't work. The liquid penetrant doesn't work. Just like visual inspection, obviously, and then magnetic particle inspection, this does rely on visual detection. So you perform the method, but then at the end of the day, a human or a person has to use their eyes to observe and then their brain to interpret what they're seeing. And so there is a potential for human error in the process. This process tends to be messy. We're working with anything that, when you hear liquid or dyes, they can stain things, they can get into different areas. You have to clean them up at the end, so it's not the cleanest process. And then Some methods, not typically ones that are done in the field, but the highly sensitive methods that are done in a lab, can be highly process dependent, and they can be difficult to perform without experience. And we'll talk about what those extra steps are and how sensitive they actually are as we get into details. So general steps, we'll look at these again, but we need to clean our part. We apply a penetrant or a liquid penetrant or a dye. We allow it to dwell, which is sit on the part and work its way into any cracks or discontinuities. We have to remove any excess using some kind of a rinse. Then we apply what's called a developer to pull that dye, any dye that's been now trapped in cracks and crevices, we pull it back out so we can see it. And then finally we do our inspection. After inspection, if the part's airworthy, even if it's not, but it needs to be shipped to that kind of thing, oftentimes you have to do cleanup as well. So there's a post clean. But let's look at the different types and methods and what are called forms of inspection, and then we'll go through the process in detail. So liquid penetrant inspection can be divided roughly into two main types, or it is divided into two main types. And this has to deal with the type of penetrant being used and the way that you view it. So type 1 penetrant provides a fluorescent indication, and so you have to view it under a black light. This is the most sensitive method. Type 1 is going to be more sensitive than any other method. But again, you have to have black light and be able to go, make a dark area in order to do it. However, the dark area, we used to do this in the hangar, and the dark area was simply, you can take like a heavy black trash bag, kind of cut it open and build like a little tent out of it, even if you can't shut off the lights. So it's not, the fact that you need a dark area isn't, and to work with a black light isn't the end of the day. You can do it in a bright hangar, even though kind of put a tent around yourself. It's the most sensitive. It can find very tiny cracks, but there is a range of sensitivities available. The more sensitive it is, it tends to be higher cost and require greater skill. The less sensitive may not find the smallest of small cracks, but they're going to be easier to perform and less expensive. And this type can be done either using portable aerosol cans or a test bench. And in lab, you'll get to use both of those. We have both a test bench and the portable rattle can or paint can method. There is also a second type called type 2, which is what's known as color contrast, or where you're able to view it with just ambient or visible white light in the room. And in this case, the dye is almost always red. It provides a red indication. And the developer creates a white background to view it on, so you get that red contrasting on white. This, however, only comes in one sensitivity level. It's known as level 1. It is portable. It's in spray cans, aerosol spray cans. However, most of your manufacturers it's not sensitive enough to be used in aerospace. Some of the general aviation aircraft you can use this on, but most of your transport category aircraft, this isn't going to be sensitive enough. And so they're going to require that you use type 1. But it is out there. It's used often for welding inspection or for, it's used probably most often for inspecting steel parts. But again, not so much in commercial aviation. So with all of these, I alluded to, they're going to have different sensitivities. So type 2 only comes in level 1 sensitivity, which is known as low. Type 1 fluorescent inspection can actually come in 5 different levels. However, they start with level 1/2. But you don't see level 1/2 very often because it's ultra low sensitivity. It comes in level 1, which matches type 2. But then it also comes in level 2, which is medium, 3 high, 4 is ultra high. What we're going to be working with in the lab, the chemicals we have, are all at the level 2 size. So they're going to find cracks in the medium range, which is what is primarily used in commercial aviation. There are, some components or some component manufacturing may use level 3 or 4 if they have to find particularly fine cracks, crevices, or items like that. So commercial aviation, we're going to use level 2 primarily, especially for anything that's done on wing, and then level 3 and level 4 are going to be used for components because there's some extra steps that are required, and they almost, level 3, level 4 almost exclusively have to be done in a test bench environment. They typically can't be done in a portable setting. So. Some of the characteristics, what makes a penetrant penetrate, and things we got to be aware of. So some of the things we got to be aware of. Surface tension is the first one. So liquid molecules in a liquid want to stick together. You know, this is like water on glass tends to bead or stick together, and we want that to happen because we need these penetrant molecules to be drawn in and out of cracks. That goes into capillary action as certain liquids are more or less capable of rising or climbing within a cavity. And so penetrants have a strong capillary action, and they tend to have fairly strong surface tension to help them pull into cracks. However, we can't have them we don't want the surface tension to be too high because we don't want the penetrants to bead. We still want them to spread out over the surface. We want them to be able to wet the surface, and that's kind of the next one. So wetting is how well it flows versus beads. So we need a penetrant that it has enough surface tension that it wants to stick together to help draw itself in as that capillary action is taking place, but not so much surface tension that it beads rather than spreading out and coating surfaces and getting into all those different areas. So we want it to have good wetting ability. And then viscosity is the resistance to flow. Viscosity can change with temperature. We've all seen that with oils. They get thicker when it's cold and thinner when it's warm. And so we want this has to have good viscosity. It has to have it has to have a good ability to flow. We don't want it to be a thick viscous fluid. We want it to be a fairly thin. So these are fairly thin oil-based penetrants that have good wetting ability. They have good capillary action. They have just enough surface tension to help them draw in, but not so much that they don't wet the surface well. So here's an example of capillary action. So when they're developing these, they have to look at how well they do work their way into cracks and crevices. And so they use something called the capillary tube, which is a very skinny glass tube. And if you put a capillary tube into like a bowl or a cup of liquid, a certain amount of that liquid is going to try to work its way up. You can see in this case the edges of the liquid are going to try to climb up the surface of the interior surface of the capillary tube. And if it's skinny enough like that, it can actually draw some fluid up with it. So the capillary tube, when you put a liquid in a capillary tube like this, the surface of the meniscus, which is in this case the bottom of the curved surface, you know, it's being drawn up on each edge, and then you've got this curved surface that sticks down. This part at the very bottom right here is called the meniscus, and you can see that's got a certain height above the surface of the rest of the liquid. And so based on how high that is, the higher that climbs, the better the capillary action of the given liquid. And so we want a liquid that's got fairly high capillary action, but it also has to be able to draw, you know, more liquid up behind it. So it has to have a certain amount of, it has to have a certain viscosity and a certain amount of surface tension in order to do that. And then there's some other things there. You know, it forms a certain angle. Theta there is the contact angle. You've got the forces working on it, gravity, and the capillary forces, what's pulling it up in the tube. So you can see this will occur in the vertical. So parts don't necessarily, when we're putting penetrant on them, you know, the die isn't just going to go in the top surface. It's not just being pulled down by gravity into the cracks. It's going to work its way into cracks, whether they're on the sides or even on the bottom. Now, it doesn't hurt to turn the part over or rotate it or move it when you're putting the penetrant on in order to, one, make sure it's fully coated, but two, help that a little bit, right? Gravity is going to help this work even better. But you will still get capillary action taking place on the sides and the bottom of the part. And it's, you know, if you're doing something on wing, it's not like you can just turn stuff over, flip it over. We had to do liquid penetrant inspections of turbine cases on our engines pretty regularly. They had a certain amount of allowed cracking on the sides, the 3 o'clock and 9 o'clock position. And obviously we're not going to be able to flip an engine or rotate an engine that's attached to the aircraft in order to get that 6 o'clock and 9 o'clock, or sorry, 3 o'clock and 9 o'clock position facing up. And so, you know, we would spray the penetrant on the side and it would still work its way into the cracks. Here's just an example of what's going on with wetting. So again, we want our penetrant to have a good wetting capability. We want it to spread out to a certain amount. However, we do still want it to maintain a certain amount of a droplet. If it spreads out too much, it'll be too thin and it won't help draw itself into cracks. We definitely don't want penetrant that forms droplets that just kind of ride across the surface and don't wet out the surface, because then it wouldn't be able to draw into cracks. So kind of having a good balance between wetting ability and surface tension in order to make it work well. When we look at penetrants, they come in 4 different what are called methods. And the method refers to how we remove excess penetrant. So when we're doing this, we're going to put a bunch of penetrant on the surface. We're going to let it sit there for a period of time, typically 10 to 20 minutes. And it's going to draw into cracks. And then we don't want all that extra on the surface. If we left all that on the surface, if we went to inspect it, we wouldn't be able to see. You know, the whole surface would glow or the whole surface would be red. And we need to see areas where that penetrant remains once it goes into a crack. So what we do is we need to wash off the extra penetrant that remains on the surface, hopefully not wash the penetrant out of the cracks that's been drawn in there using capillary action. And so that wash can take place using 4 different ways. So method A is known as water washable. Method B is what's known as a post-emulsifiable lipophilic, and lipophilic refers to the type of molecule. We'll talk about that in a second. Method C is a solvent removable, so we actually dissolve, instead of rinsing it off, we actually dissolve the excess penetrant off. And then method D is another post-emulsifiable, but then what's called hydrophilic. So what does that mean? So penetrant methods B and D, these are known as the post-emulsifiable methods, there's an extra step in these, and these ones are almost always performed in a bench or in a lab environment. Okay, so in my brief summary, I said we clean the part, we apply the penetrant, we allow it to dwell, we rinse off the excess, we apply a developer, we allow it to develop for a period of time, and then we look for indications. With a post-emulsifiable method, we have an additional emulsifying step between the penetrant and the developer. So in the case of these, we would clean off the part, we would apply the penetrant, we would allow it to dwell for that 10 to 20 minutes, but then before we can remove the excess, we have to apply an emulsifier to allow us to remove the excess. And then we're going to rinse the part off, clean it off, then we're going to apply our developer, let it sit for 10 to 20 minutes, and then we're able to do it. So these are used where there's a concern of overwashing a part, or if we need basically extra sensitivity. So when I was talking earlier about the different sensitivity levels, a half, 1, 2, 3, and 4, to get to a level 3 or a level 4, that's where you have these post-emulsifiable methods. Whereas the water wash and the solvent removable, those are going to be your level half, 1, and 2. So it allows us, the idea here is we put on a penetrant that's very hard to rinse off with water because they're oil-based. We put on an emulsifier, which allows us to use water to remove a oil-based item. And for those, most of you are probably familiar with an emulsifier you have in your home, and that would be dish soap. right? You use dish soap to get the oil and the grease off of your pots and pans and plates and whatnot. That's an emulsifier that allows water to rinse off or bind to and remove oils. And so it allows for the breakdown and wash away the extra penitent. Now, the downside to it, though, is it's very easy to over clean, especially with method B, which is lipophilic. And what that means, lipophilic versus hydrophilic, lipo means fat or oil. Okay. Philic means attracting or means to bind to something. Okay. So method B with lipophilic emulsifier, the emulsifier, this third liquid we use, wants to bind primarily to the dye, to the oil-based dye. But it also will bind to the polar water molecules to allow it to rinse off. But what that means is it's very easy for that, because that lipophilic emulsifier wants to go after dye, it will, if it sits on the part too long, it will start to go down in the cracks as well, and it will pull the dye back out of any cracks and crevices that we're trying to find. Method D, the hydrophilic version, tends to bond more strongly to water. It still bonds, it still allows the water and the oil to bond to one another, but in this case, the emulsifier primarily bonds to the water, but then allows that to kind of grab the dye. And so it doesn't pull the dye out of the cracks as much, but it does allow it to be removed from the surface, which is the whole goal of this process. Method B is older. That was the original emulsifiable version. Method D, hydrophilic, is a more recent development, and nowadays method D has all but replaced B because it's more forgiving, it's more sensitive, and it's easier to do correctly. In fact, method B, when it talks about the wash time and the emulsification time being critical with a lipophilic, it can be a matter of a few seconds during the process of whether you did it properly or did not do it properly. It might be a matter of 2 to 4 seconds. Method D, hydrophilic, it can be a matter of 30 seconds to a minute. So you can see why they don't do method B very often anymore. We won't be doing either of these methods in class. We'll be working with method C, and then method A we'll talk about in a minute. So solvent removable method, it's more sensitive than method A, which is water wash, but it's less sensitive than the methods B and D, than the emulsifiables. Okay, so it's solvent removal. What that means, a solvent breaks down an oil. So it's emulsifier bonds, allows water and oil to bond to one another. The solvent actually dissolves or breaks down the oil molecules, the hydrocarbon chains that make up the oil. So it's going to be more sensitive, but it's also very easy because it does break down the dye. It's very easy to overdo it and to ruin the dye or to dissolve the dye that's in the cracks and crevices. So we have to take care. We want to clean the extra dye from the surface, but we don't want to clean the dye back out of the cracks while we're performing our inspection. Once everything's done, we can use the solvent to clean the dye out of the cracks after we've done our inspection. And this is most often used for aerosol and portable applications. And this is what you'll be doing when you do it in class in the portable aerosol. Method A is the least sensitive, but it's the most forgiving, because here you're basically using a water to wash off an oil-based dye that has an emulsifier built into it already. So there's kind of an emulsifier built into the dye. It allows it to be washed off, but typically adequate for most inspections. It's very reliable, easiest to do. It's fast, but you have to match your sensitivity of your penetrant to the cracks that you're expecting to find. And so it's a little more critical in that you have the correct penetrant for what you're looking for. But just keeping in mind that a more sensitive penetrant is also easier to screw up. It's harder to do correctly. And so the water wash method is what we'll be doing in our test bench. That's what we have. Many penetrants actually can be multi-method. So the penetrant we're using, that's in the type 1 penetrant we're using, that's in aerosol cans, is actually the same penetrant that we have in our station. So when you're using it in aerosol cans, it'll be It'll be a method C with aerosol cans and aerosol solvent. When we use it on the test bench, it's going to be a method A, even though it's technically the exact same dye, just whether it comes in a big jug, a 5-gallon jug, or comes in a spray can.